Yeah. Okay, welcome everyone to Physics 3102 Quantum Transport. This is my very first class as a professor, and it's a first lecture that I give. So it is, hi, come on in. So I'm very excited, and I'm doubly excited because I have a chance to give this class on a topic that is dear to my heart and is closely related to my own research, and I know that it's closely related to the research of many of you, and for those of you who come from other disciplines, I hope I will be able to make you excited about this wonderful field of physics. It's not, I think as of a few years ago, it is no longer a subfield, but is a fully fledged independent field, which is very important in modern science and potentially in technology. Today's lecture is an introduction, and it will be about the scope of the course and of this field, and to get all of you also excited for the upcoming semester, and I will explain how the course will proceed and give you some examples of what I mean by quantum transport. Okay, we meet twice a week. There was a typo on the web. The course actually goes till 2:45, not 2:15, so it's a little bit longer than some of you might have thought. Yes, my name is Sergey. Please just call me Sergey. We are all upper level graduate students, so no need for ceremony. You can feel free to stop by my office or by my lab or send me an email anytime you want about the course. Any questions you might have, I'll be happy to answer them. Okay, first of all, there is by now quite a bit of different literature on quantum transport, and the synonyms for this field, such as nanoscale transport, mesoscopic physics, those are all mean roughly the same thing. So there is a number of very good textbooks, and here I list all the literature that I think you could find useful, though I think course will be largely self-contained, but I think to get more background and to have something to read, I strongly encourage you to look at these books, and some of them, especially these upper two, are available at the library and also in my lab, so you can come and borrow and send me an email if you want to use these books. So I listed them in a chronological order. The upper two are the most recent ones, and they also make a very nice set, because this book, Quantum Transport, it is written by theorists, and so it has a lot of formalism and equations and consistent approach. So for those of you who are theorists, you might enjoy this book more. And this book is written by a career experimentalist, a very excellent physicist, but also a great teacher, and so he focuses on experiments that are key to this field. At the same time, I want to say that none of these books is complete, otherwise I would have given you one. For example, in this course I'm hoping to touch on some of the effects related to superconductivity, but this book strictly talks about semiconductors. So some of the effects are not in this book. Okay, now here are three other sources. These are a little bit more dated, so they don't have all the most recent experiments, but they are very good. These are lecture notes from Delft University, which I might be able to offer you if you ask me for them. So the course will follow these in many instances, and these are written very well for graduate students who are starting in the field, so this will be a good option. This is a very famous textbook in our field, which explains some of the similar stuff to this book and this book. It is written by a theorist who is in electrical engineering, so it combines kind of the approaches of these two books. This one is open source. You can find it on the archive. And this is already 20 years old, but it summarizes the foundational experiments that were done in the 80s and early 90s in the field of quantum transport. I have the pleasure of knowing most of these people, actually personally. So I don't know Supriyo Datta, though I've attended his seminars. But I've worked with Yuli Nazarov and Blanter and Carlo Beinacker in Delft. I know Thomasin, and Kees Harmans is also from Delft. So actually a large fraction of this material is from the Netherlands, where I used to work before coming to Pitt. That is perhaps a coincidence, but it also allows me to understand very well what these people are talking about, and hopefully you will enjoy these books as well. And some of the lecture slides and notes that I will be showing are also from courses, similar courses developed in Delft and in Eindhoven in the Netherlands, but of course they are reshaped for my view of this field. Okay. The course mostly relies on the knowledge of the basic quantum mechanics. Yeah? So not even the advanced quantum mechanics, but the simplest concepts, such as representation of particles as waves, confinement, quantum confinement, so particle in a box problem, and the box can be one-dimensional, two-dimensional, or three-dimensional. Those are very important examples. Yeah, waves that are free propagating, and things like two-level systems, for example, spin one-half physics, dynamics in two-level systems. This will become important later in the course. A little bit of knowledge of solid-state physics will be very helpful, though I will probably try to cover most of it. But if you have some idea about band structure in metals and semiconductors, about the behavior of Fermi electron gas, density of states, if those concepts are familiar to you, it will be easier for you to navigate the course. Actually, this is very remarkable that so little background is needed to understand such an advanced field, which is at the forefront of modern science. It is enabled by modern technology. So all these very simple concepts, you can actually literally implement them in real nanoscale devices. So you can actually observe the most simple examples from a quantum mechanical textbook, which maybe at the time where you've taken a quantum mechanics course, you would have thought that this is a completely Gedanken experiment, such as quantum levels of a particle in a box, etc., etc. But here, with a new technology, which I will highlight today a little bit, you can implement the simplest models, such as an electron propagating in a straight line, like in a waveguide. And so this is why we don't need to go into too much details of these solid-state physics as such in this course. Okay, there will be homework. This is an advanced course, but I think this homework should be fun for you, and homework as well as the final exam will be like playing a professor. So like kids play a doctor, or they play in a store, or they sell and give goods. We will play a professor. So we will review real scientific papers, and we will also write proposals for experiments, right? So we will do some of the components of a principal investigator. Yeah. So the homework is that you should pick up one paper It could be recent, could be old, but it has to be on this website. Yeah? Pick one paper, read it, try to understand it. You don't have to understand it fully, but make some effort, and then write down your thoughts. They could be just something like, I didn't understand anything, but I have these questions. Or it can be a full evaluation of the paper. The paper is flawed in such and such way, it is not a good paper, or this is a wonderful paper, a template for everyone to follow. So anything like that counts. So this is like a review that someone would submit to a journal, like a referee report. But then you will not just send this report to me. You will post it on a new experimental platform, what we call Archive+. I will show it in the next slide. But basically, it is this website with the ability to comment on papers. Yeah. So then all of you will see each other's reviews, and you can also engage in discussions. Like, for example, oh, I disagree with this review. I think this is a wonderful paper. Or you can answer each other's questions. If someone didn't understand the paper, maybe another person understands. So this kind of interaction. You can also just evaluate papers with one click, like on Facebook. You can add a like to the paper. This Archive Plus is something that we started with a couple of PhD students in Delft. And now we are in a testing phase. Yeah? So you will be the focus group. So at the end of the course, I would appreciate if you have any thoughts, feedback on this idea, on the implementation as well. I would appreciate that. So this is how it looks. This is going to be your homework. How many of you have looked at archive.org at least once in your life? 100%, excellent. So basically, all of you recognize this template. This is the red bar and then the abstract of a page of an archive. And here you can download the paper and read it. Now, what the Archive Plus does, it gives you the same web page, but it adds certain elements. So in this design, they're marked with little pluses. Yeah, so at the front, you have at the top, you have a certain menu, but here, we added a little square where you can like and add the paper to your library if you want to read it later. And here at the bottom, you can leave your comment. So here, this paper, I found it interesting, and I left a comment here. Yeah. So by the way, I will also participate in this, and I'll try to get your supervisors to join this website. So we have some critical mass, and we have fun with it. Yeah, so here I left a comment. I will not show you the whether I liked the paper or didn't like the paper. But in principle, this will be, for now, a closed project, so you can express your opinions freely. The authors of the paper will not see them, unless you comment on each other's papers, of course. And the way it works is it is a shell through which you browse archive. So if this is archive.org and it has a storage for papers with abstracts attached to them, then when you log in through Archive Plus, it retrieves papers from archive.org. Yeah? And then it adds in your screen, so it's like a proxy server, right? It adds in your screen the ability to do all these things. Yeah? So it is like a small social network for scientists where we can quickly exchange opinions about the papers. Yeah? Ideally, you put something on the archive, and then boom, you get 10 comments the next day, if it's an interesting paper. So this will be the homework. I propose that we do one review per week, yeah, per person. So we will have some fun with it. And the final project is a proposal for a new experiment. Yeah? So by the time that we finish with this course, we will know the scope of this field, and we should be able to come up with a new idea. It's not been done before, that is interesting to try, to at least to think about. Maybe it's not completely realistic, but a little bit feasible, yeah, and it should be exciting. I will help you throughout the semester, so you can talk to me about your project. One important condition is that it cannot be strongly connected to your current PhD research. Yeah? So that makes it too easy. Maybe you have been in your group for a couple of years, you thought about your project, and you already have an idea that is ready to go. We will not allow that. So it has to be from another field, but from the area of quantum transport, which is pretty big. And yeah, we have plenty of time to come up with it. And importantly, it has to be an experiment. Yeah, so not a theoretical idea, or I will propose a certain calculation, but it has to be a measurement. And this is related to the main focus of this course, which will be an experimentalist perspective on the field. Yeah, so the bulk of the course will be about me telling you about various exciting experiments from this field that shape the field, and the concepts that we need to understand these experiments. Yeah. So this will be an experimental course focused on also a little bit on methods which are used to do experiments, and also on staring at the experimental data, trying to read into it, trying to read enough into it but not too much, and things like that. Okay. So this slide is designed to illustrate the difference between classical and quantum transport. Yeah? The quantum transport is two words, quantum and transport refers to the type of measurement that we will be studying. It is always basically the same measurement. It is a study of how charged particles flow through a conductor. Yeah, so the most basic example of transport is when you hook up a battery to a resistor and you measure the current that flows through this resistor. This is a transport measurement. Of course, unless it's a very special resistor, it is a classical transport measurement. And that is because electrons, when they flow through a resistor, maybe at room temperature, for sure they can be regarded as little balls, particles, and not as waves. Yeah? So to go to quantum transport, electrons or holes, charged particles flowing through our conductor have to behave like quantum mechanical objects. Yeah? So for example, here are two samples which the shape of them looks identical. It is some sort of a two-dimensional cavity. It is a rather perfect cavity because here in the classical regime, when an electron enters into this cavity, it just bounces off the walls. There is absolutely no scattering or interaction between different electrons. So this is a ballistic cavity, but it is classical because all we need to know about transport of these electrons to model them is that they are particles with a certain velocity and they bounce in this cavity. Yeah, so then if we know that and the shape of the cavity, we can calculate what will be the current flowing through this cavity for a given voltage bias that is applied to the cavity. Now this is an example where we have done something to this system, and the same sample, we cannot anymore treat this electron as a classical ball, but we have to describe this entire cavity with a wave function. Yeah, so this is an example of a wave function formed by interferences of electron living inside this cavity. So then the proper description for this sample would be that a particle enters this wave function, and then it has a certain lifetime inside this wave function, and it tunnels out. And in principle, if we had a probe, maybe some needle that comes in from here, we could map out this wave function, where it has peaks and where it has dips. And so the field is dedicated to finding that actually when you have to use a wave function description of electrons, then many non-trivial and often counterintuitive effects can be observed in real samples. Yeah. So what can someone name me one reason why this electron would stop being a little ball, classical particle, and go and become a wave function? What can we change to make this happen?
Shrink the chamber.
Shrink the chamber to make it smaller than the wavelength of an electron, for example, right? Yeah, that's a good one. Other ideas?
Lower the temperature.
Lower the temperature, exactly. Temperature is an energy scale, and it smears the quantum effects. Yeah, so the high temperature makes quantum objects look classical. So you would have to shrink the temperature such that the energy scale related to this wave function is larger than the temperature. Yeah. Okay. So we already just with these two examples, we have determined that we have to be probably at some low temperature to study quantum transport, or we have to study small objects, maybe nanoscale objects. Yeah. Okay. Just at the beginning of the course, I want to show you a couple of slides that provide a real-world motivation for these studies beyond fascinating fundamental physics that can be discovered. And it's first and foremost the progress in electronics. Yeah? So you probably all seen some version of this graph. This is the Moore's law, as postulated empirically by Moore, that every 2 years the number of transistors on a chip doubles. Yeah? And we are still living in the Moore's law for already about 50 years, and it is expected to continue like that for at least a few more years. And basically it is important for the semiconductor industry, for information technology, to continue this law, because if you make more transistors and if you make them smaller, the computers become more powerful. Yeah? So the smaller transistors means that electrons can cross them faster, and that means we can increase the frequency of the transistors. Yeah? And more transistors means we can do more calculations, maybe simultaneously. Yeah? So it's very important for various applications in this industry. But since we were following this law already for 50 years, we have gotten to a stage where the circuits that actually in any of our computers, or even by now in our cell phones, are extremely complicated, and they're also extremely miniaturized. Yeah? So this is a one Intel chip which has, I don't know, billions of transistors on it, and so it is a highly complex circuit. But if you look at just one transistor, yeah, a transistor always has a source and a gate and a drain. Yeah, so then just one transistor in this circuit has already become so tiny, yeah, that here are some numbers. The channel length, so the gate length, is 32 nanometers. Yeah, so we are in a nanometer scale, and we are not too far from the wavelength of an electron in a semiconductor. Yeah, actually, in fact, we about the right size for that. And so we are already dealing with a nanotechnology here, and we must already include quantum effects when we think about how these transistors function. Yeah. And so it's important to understand what happens if electrons are considered as quantum mechanical objects to improve the performance of CMOS technology. So here is a specific example which also shows some of the challenges for going further with CMOS. And this is a computer simulation of a single transistor, a single MOSFET transistor, metal oxide semiconductor field effect transistor. Yeah. So it has important elements, source and drain, so you can send electrons in and then they go along this channel here from source to drain, and then there is a gate which can change whether electrons go through or not. Yeah? So it's an electrostatic gate, like in a capacitor. It can change basically the occupation of electrons underneath the gate, and so it can completely block the transport or it can enable the transport. Yeah? So the concept of gate is very important throughout this course. And the gate has become so small that just a number of dopants that induce electrons in this channel is in the tens. In this simulation, it is 36 dopants. Yeah? So we are really dealing with a discrete number of quantum particles, atoms, electrons, in the modern transistors. And so not only the quantum mechanical nature of these particles is important, but also the imperfections that come from the quantized nature of the number of these particles. So for example, in this transistor it's 36 dopants. In the one next to it, it could be 30 dopants. And in the one next to it, it could be 45 dopants. So these fluctuations are a big problem in the field, and they're also often encountered in quantum devices that we will consider. Yeah, so the description for such devices is very different from the classical approach, where you can exactly calculate all your properties. Now this is an example taking this to the extreme. This, especially the upper one, this is a transistor that consists of a single atom. Okay. This is a single impurity of phosphorus on the surface of silicon, and this one is conducting. So what you do is you come with your electrons from here, you hop onto here, then you hop off and you continue. So this transistor consists of a single atom. Needless to say, electrons also travel through this transistor one by one. So what is also important here is the charging energy of an electron. So the reason why the two cannot go is because it costs so much energy to put an electron on this island that if you put a second electron on this island, you just don't have the available energy. So this device is obtained by with a STM technique, so scanning tunneling microscope. It also provides this image with an atomic resolution, but it is also used to implant the phosphorus here. I will not go into details, but you can look up the research of this excellent group. And so by this they can define single atom transistors. So of course this is not scalable to billions of transistors yet. You cannot send a needle and implant 1 billion of these atoms, but as a powerful demonstration that you can scale the transistor down to the ultimate quantum limit. And this is not a real picture but a cartoon, but it is from Pitt. And this is a similar concept. These green atoms designate the points for the island of a transistor. This is not a single atom transistor, but this is a few atom transistor that we have access to here in Pittsburgh. Okay. So what I told you is that the people in the semiconductor industry are interested in quantum mechanical descriptions of electrical devices in order to better understand the circuits that they are already working with. Yeah? But they're also looking at devices, and that is to enhance the functionality of their circuits beyond what they can do now. Yeah? So for example, currently the backbone of all this technology is a transistor. Like I explained, it is a gate, source, and a drain. But what if a gate is also spin dependent? So you're adding another degree of freedom into the functionality of this transistor, which can allow you to maybe implement a certain logic gate with these transistors with fewer operations. Yeah? So new functionality that is not there in CMOS is one of the focuses of this International Technology Roadmap for Semiconductors, ITRS. This is a very important document that drives the development of not just industry but also research. In particular, they have a whole subdivision which is designated to beyond CMOS ideas. So the spin gate is one idea of something where you go beyond CMOS, and you can build computers that work on fundamentally different principles inside. And this ladder of concepts summarizes the 2011 vision of ITRS beyond CMOS. And these are kind of a scatter of keywords, but if you just stare at them, you will find many of the words that are relevant to this course. Of course, quantum, quantum state, quantum, but not only. Nanostructured materials, spin orientation, strongly correlated electron state, carbon, yeah, spintronics. So trying to do different new materials, and also quantum is prominently featured in this ITRS. Right? So this is this shows you what they're thinking about going forward, yeah? Going beyond CMOS. Okay, so once again in this course we will study transport, so passing of charged particles through certain samples. And we will study them from the quantum mechanical point of view. And the concepts that I'm hoping to make firm in this course are, first of all, quantization of various electrical properties, for example, conductance, charge, magnetic flux, in low-dimensional systems in particular. Yeah? So I will tell you that a lot of these experiments are done in systems where electrons are heavily confined in 1, 2, or 3 dimensions. Then phenomena related to quantum interference. Remember I showed you this cavity with a wave function that looked rather chaotic. Well, that is due to interference of electron with itself. And so many of the quantum transport phenomena are interference phenomena. And finally, quantum tunneling and Coulomb blockade. The example of a transistor where in the center you have one atom and the source and the drain are disconnected. How does the electron get from the source to the island and out to the drain? It tunnels. Yeah? So quantum mechanics comes in a transport of electrons through disconnected parts of a circuit. And you can still cross them with tunneling. And these are the core concepts, and then we will develop towards new experiments that are done these days, and those involve superconductivity, quantum computation, and maybe a subset of that, or maybe an independent field. At the end of the course, we will touch on the new topological effects. Okay. So this slide shows where concepts like ITRS roadmap for semiconductor industry and the fundamental physics meet together to form a happy marriage. Yeah? So a number of fundamental fields that we study in the lab may find applications in real computers or other devices in the future, and therefore we get extra support for working on these ideas, even if we're just interested in their fundamental value. So first of all, probably all of you heard about at least quantum computing, but maybe the other ones. So quantum computing, a way to store and process information in quantum mechanical degrees of freedom using concepts like superposition and entanglement to boost computational power for certain algorithms, right? Not for everything. Spintronics, like the example of a gate that is spin dependent, or transport resistance of a channel which is spin dependent, embedding extra degrees of freedom into transistors and elements like that, or using spin from memory is another example of spintronics. But from a fundamental point of view, studying the behavior of spins in solid state down to the single spin level, and controlling single individual spins with external controls, that is also in the realm of spintronics. Optoelectronics is one example of a bigger field of hybrid technologies where different degrees of freedom are combined in a single device. Here we might send in a single electron and get out a single photon, for example. But what if we now take an electron with a well-defined spin and get out a well-defined polarization of that photon? Yeah? Or what if we take an electron which has a superposition of spin states and transfer that superposition into a superposition of polarizations of a photon? Yeah, so this is one example. Other examples of hybrid techniques are something like nano-mechanical, nano-electromechanical systems where transport of electrons drives a mechanical mode and maybe down to the quantum level. And there are other examples. Okay, so classical transport. The best known example is, of course, Ohm's law, right? And Ohm's law is just a linear proportion between voltage and current. It's rather boring, but rather universal, and it takes a lot of effort to make something that deviates from Ohm's law. And we will almost entirely study devices that completely violate this law in every possible way. And the quantities that will govern whether devices violate Ohm's law, and also that will just show up in the measurement, like steps or interference patterns in the data, are these three quantum values. Yeah? They all consist of fundamental quantum constants, and they're very important. So for, of course, the quantum of charge, if we can observe transport of electrons one by one through a certain structure, we will immediately see that the transport properties such as conductance, current, voltage are quantized in the units of charge. This one is a little bit less trivial. Apparently resistance, or better yet conductance, can also be quantized. Yeah? The quantum of conductance, this should be G, I apologize, is just E squared over H. Yeah? So if you work out these units, this will be 1 over ohm. And it is this messy value, so it's much easier to remember a quantum of resistance, which is about 26 kilo ohms, 25.8 kilo ohms. Yeah? So for example, if a resistance of a system is smaller than the quantum of resistance, then maybe the system will behave classically. If the resistance is higher, some kind of quantum effects might show up. And finally, quantum of magnetic flux, just E over H. This governs the various interference patterns of electrons as they travel through the sample. And it is, in these units, it's 4 to 10 to the minus 15 Weber. Now, I told you that you can directly see all these three values in experiments. Here's a proof of that, this is from Thomas Inn's book on semiconductor nanostructures. These are 3 examples of real experiments. This is data that each show a quantization of one of these quantities. So maybe let's go through them together, because maybe some of you already know what these are, or maybe we can guess. So let's start here. Who knows what this experiment is? You don't have to know, you can also guess. So we have to look at the axis, and this is a picture of a device. I need any guess which area this relates to, or?
Hall effect. Base is the next one.
Maybe this one.
Yeah, this one also.
Yeah, so resistance is oscillating as we change magnetic field, and the sample looks like a ring.
Lambda. It's not Lambda level.
Well, Landau levels don't require a ring. They will just appear in a bulk. Any more ideas? Okay, I will explain. So this first one is okay. Let's at least can you at least someone tell me what is quantized here? Charge, conductance, or flux? Flux, exactly. Magnetic flux is quantized. The quantization of magnetic flux can be read out from here. So the sample is a ring, and you can send the electrons from here to here, and you apply magnetic field like that. Yeah? And the thing is, this ring, this entire ring, is smaller than the wavelength of electrons. Yeah? So it is a quantum regime where electron can go through the entire ring, but it is one wave function. Yeah? It is in other words, you can say that the dephasing length of the electron is longer than this structure. Yeah, so then what does this electron do? Well, it can go via this path through the ring, or it can go through this path through the ring. Yeah? Well, which path will it go through? Both. Yeah, it is a quantum mechanical object. So it will go through both parts, and at the end, at the drain, it will reunite with itself, and it will interfere with itself. That's right. So then we have to, for the interference, the important value is the quantum mechanical phase. Yeah? And in general, electron will acquire a different phase going through this side of the loop or going through this side of the loop if there is magnetic field present. Yeah? So if the geometry is perfectly symmetric, maybe it will get the same phase and we will get constructive interference at the end. But if there is magnetic field present, then we have to include the gauge vector potential in the evolution of this phase, yeah, and that is called the Aharonov-Bohm effect. Did you hear about the Aharonov-Bohm effect? Some of you, not everyone, most. It's important for me to know because then I can adjust the course so that we cover the right concepts. Yeah. So then this is a vector potential is a gauge field, and so it has to be periodic, and it turns out to be periodic in the units of quantized magnetic flux. Yeah? So for whatever the area of this loop, as soon as we put in one unit of magnetic flux, the system should remain, should come to the initial state where it started. And that's why we get these oscillating patterns. Now, another important concept that this device, that this experiment transmits, is that resistance, yeah, something you measure with a voltmeter or current meter, is dependent on the interference of electrons. Yeah? So for example, maybe if the interference is destructive at the drain, will the resistance become higher or lower?
Higher.
Resistance will become higher, that's right. So because the wave function will have a minimum here, yeah, and it will be more difficult for the electrons to come out. Yeah? So if the interference is constructive, maybe it is easier for them to come out. And so the details of this pattern are a separate field of study. Why are these wiggles have this magnitude? Why do they show another modulation? What is the role of these other exits? We can just dedicate a whole lecture to Aronoff-Bohm effect. But just for the beginning, for the first lecture, just wanted you to get this flavor of this effect. As an exercise, let's estimate the area of this loop. Yeah? So there is no length scale. We cannot see the length scale, but we know that about 5 millitesla put in one flux quantum in this loop. And the flux quantum was 4 times 10 to the minus 15. Yeah? So let's say 5 times 10 to the minus 15 for simplicity. These numbers work out really well, actually.
You need the area.
Well, area or dimension, either way.
So F0 divided by 10 million Tesla.
Well, let's say 5.
5 will be 10 to the power of minus 18 centimeters squared. So I divide F0 by B, the magnetic field, and I get the area.
Yeah, so what we have to do is flux phi 0 is B times A. Yeah, so area is phi naught over B. So this is 10 to the minus 15, and this is 10 to the minus 3. So this is 10 to the minus 12, which is 1 micron squared. Yeah? So the dimension, the characteristic dimension of this loop is 1 micron. So this must be a semiconductor, because in a metal there's you can still get a coherence length this long if you cool down the system very low. Yeah. So we don't know what this system is, but it looks like a semiconductor to me anyways. All right, so quantized flux. Now, who knows what this effect is?
Quantum Hall effect.
Quantum Hall effect. That's right. So here we have, as a function of now very large magnetic field. Let's not go into why this happens for now, but we tune with a control knob, which is magnetic field, through, this looks like a staircase of resistance. Yeah. Now let's not look at this. This is the actual Hall part of the quantum Hall effect, which shows little spikes in Hall voltage. But let's not look at that. Let's just look at this staircase of resistance. Yeah, so the question is, what is this staircase? Why do we have this staircase? Okay, this is a bad way to ask this question. What are the values of resistance that correspond to this staircase? And so it doesn't look like the resistance is quantized actually, huh? So we should, if resistance were quantized, we should see steps of 26 kilo ohms. Here we have steps. First of all, there are steps of different size, and they don't correspond to any 10 kilo ohm scale. They correspond to, well, actually just 1 kilo ohm scale. So who can guess what's going on here? Well, this is somewhat tricky if you haven't thought about it long enough. But basically, there is another value which is quantized. And if you replot this graph, you will get perfect steps which are all equal. Exactly, yeah. So what is quantized is conductance in this case, not the resistance. Yeah. So quite often you see that the conductance is quantized and the resistance is not quantized. And the reason for that is fairly simple. And I don't expect you to explain this to me because I didn't tell you what quantum Hall effect is. But quantum Hall effect is conductance or electrons that flow through a number of quantum mechanical one-dimensional channels. And each channel has a quantized resistance of R0. But electrons can flow through them in parallel. So to get the total resistance of these channels, we have to add them like that. Like parallel resistance. Yeah? But this is actually a quantum of conductance. Yeah? So in the language of conductance, it is much easier to deal with this effect. We just have to add up the conductances of all the channels, and we will get the total conductance. So basically, if you look at the quantum Hall trace, and you invert this scale, then these will become perfect steps of conductance. But you can estimate how many channels are here, for example, at the top of the graph. Yeah, because here you have something which is of order kilo ohm, and conductance quantum is 20 kilo ohms. Yeah? So that means we have on the order of 20, a little bit less, conducting channels at the top of this graph. Okay, finally, this graph shows, well, I will not tease you, this is charge quantization. Yeah? This is the only one left. So, but this is a very interesting and a very important effect, which is called Coulomb blockade. You know? And it is related to the fact that if you have an island, disconnected island of where electrons can live, it costs you a certain energy to put electrons on this island, and it is the capacitive energy. It is E squared over C. That's the capacitive energy. And so what this sample is, it is again a semiconductor structure shaped by gates. So these are metal gates on the top, and the electrons that we care about, they live underneath the surface. And so we can create a pinched off island here by adjusting voltages on these gates. So what you have to look kind of through this pattern and think of a little island, again of the size of a 1 micron, which is disconnected from these contacts. So then these will be source and drain, and the connection will be via tunnel barriers. And the tunnel barriers are just created by these gates by making negative voltages and preventing electrons from freely flowing through. And now here the control knob is another gate voltage. And this gate voltage, it is a plunger. It is a jargon for plunging electrons out of the dot. So what you see here is, as you make the plunger more negative, you kick the electrons out of this island one by one. And the way you do this is by, you can think of it two ways. Either by making it more negative, you shrink the size of the islands and electrons just don't fit so they come out. Or you can think of it in terms of energy. You change the energy of the electrons, the capacitive energy or the chemical potential, by adding electrostatic energy from the gate. Yeah, so we will come back to such structure many times in this course, so you don't have to understand it fully. But let's just look at the data, and it shows peaks, and in between the peaks there is no conductance, and peaks are in conductance. Yeah? So that means that at each peak it costs you equal energy to have n electrons and n+1 electrons on this island. And therefore, you can freely add electrons and they will come out. And that means you can have transport. Yeah, so certain energies are equalized. And that gives you a peak in conductance. And then when you tune away from the peak, that means that it costs you extra energy to put electron on the island. And the transport becomes blocked. Current becomes zero, conductance becomes zero, and that is called Coulomb blockade. And so a presence of a single electron on this island can completely block the current, and this is very against Ohm's law. Right? Whereas in Ohm's law you can put as many electrons as you want through the island, and they will just come out after bouncing inside the island. So quantized flux, quantized conductance, and quantized charge can all be seen in semiconductor nanostructures. And of course they're semiconductor because they're from a book which is called Semiconductor Nanostructures. Okay. The field is 20 to 30 years old, and this is about the time scale going back in time when people started observing quantum mechanical effects in electrical measurements. Effects like interference and quantization. So for example, quantum Hall effect was discovered in 1981, exactly 30 years ago. So that is the time scale for this field, and initially quite naturally the field has to establish the basic effects, such as, okay, electrons are waves, they have mass, they have spin, they have charge. What happens? Yeah, so those are examples of these very basic effects which just tell you that electrons can interfere, conductance in one-dimensional channels can be quantized, and charging energy is an important energy scale. And let's call these basic electrons. Yeah, that have just these properties. And they can be used to describe these very important concepts. And this will be roughly the first part of the course, throughout which we will study the foundational experiments in quantum transport, such as the ones I showed in the previous slide. But 30 years is a long time, and it can also get a little bit boring studying such basic electrons. Now, how many times can you see interference over and over again? And so lately, a lot of effort has been dedicated to these more amazing electrons. Yeah? They're actually the same electrons, but you kind of pull out extra blades from the knife, and you include various interactions and band structure effects into consideration, and you also use these extra tools as functionalities in your quantum devices. So this is again a happy marriage where we can understand more about the condensed matter systems that we're studying by including these effects. And these are only some examples, though very important ones. But also we can build devices that exploit these effects in their function. Okay, let me see. Okay, we have 15 minutes. I want to go through them one by one because I think they're quite important. So this one is actually still borderline basic electrons. Yeah, but I think it is a little bit non-trivial and so worth mentioning. So in free space, electrons are fundamental particles described by Dirac equation and included in the standard model. And those electrons have the well-defined mass of an electron, a certain charge, certain spin. Does not have to be the case in semiconductors. And primarily, the mass of an electron can be very different from the mass. For example, in these important semiconductors like gallium arsenide, which is actually the semiconductor which probably gave rise to all of these three curves, a mass of an electron is much smaller than the mass of a free electron. And one thing that it gives you is actually, I think, higher mobility for these electrons. So it's good for electronics to use gallium arsenide. But another thing it gives you is that mass, smaller mass, makes the wavelength larger. These are lighter particles, so it's easier to make them quantum. Yeah? So we can think of quantum devices which are bigger in this semiconductor. And this idea is kind of taken to the extreme in graphene, where I'm sure many of you know that the mass is 0. Yeah? So these electrons are, in graphene, they're sometimes called relativistic particles, because this is the relativistic Dirac equation that gives you a 0 mass for these particles. And so some of the quantum effects, like quantum Hall effect, in graphene you can see it at room temperature. Now, electron-electron interactions, that is a very large area, and in principle, Coulomb blockade is an example of electron-electron interaction, because the electron is sitting on an island and it is not letting other electrons on. So that's an electron-electron interaction. But it is quite natural to consider this interaction, especially at low temperatures, and it gives rise to many interesting effects. For example, sometimes the quantization of conductance is not in the units of one quantum of conductance, but in the units of 1/3. So this is kind of easy to explain by having particles of charge E travel in independent channels, and then you get this quantization of conductance. But in fractional quantum Hall effect, there are fractions like 1/3, 1/7, 1/5, these kind of fractions, and they correspond to actually fractional charges. Yeah, so by including electron-electron interactions, you can even take one electron and kind of split it apart, which you cannot do with elementary particle electrons in free space. So this is quite fascinating. Kondo effect is another interesting example of interactions where if you have an electron with a spin sitting on an island, electrons around the island gather together and screen the spin. So this is a strongly interacting effect. Hyperfine coupling. This relates to a very important area in condensed matter physics, which is interaction of one particle with many. Interaction with a bath of degrees of freedom. In this case, it's a spin bath of nuclear spins. Hyperfine interaction in condensed matter is a little bit different from atomic physics, where electron in an atom interacts with a nuclear spin of that atom. Yeah, in condensed matter physics, because electron overlaps many atoms, then one electron can interact with 1 million nuclei, which are within the wave function of an electron. Yeah. So then you have to calculate the ensemble averages of coupling of an electron spin, of a single spin, to many, many spins of the nuclei. So this interaction is very important in the context of spin qubits, because coupling to these various embedded spins makes the qubit decohere, perform poorly. So this is an important problem to understand, but maybe it can also be used as a spin memory. So for example, if you can use one spin of one electron to control 1 million nuclear spins, you can transfer information into these nuclear spins, store it there, and then extract it back. Spin-orbit coupling. This is, again, sort of a band structure effect, but I put it separately because it is becoming very important recently, especially with topological phases. But basically, it is a very simple effect. A spin of an electron is coupled to the motion of an electron. Yeah? So if the electron flies this way, the spin of an electron sees a magnetic field maybe this way. But if it flies back, the magnetic field is this way. So then by controlling how electrons move, the spin can be controlled. Or by controlling the spin, we can control how electrons move. And this is, like I said, important interaction for qubits and for topological phases from topological insulators, Majorana fermions, and spin Hall effect, and many of the recent developments in quantum transport. And superconductivity is another type of interaction where electrons interact pairwise to form spin singlets called Cooper pairs. And when you go from one electron to two electrons coupled, then these Cooper pairs become bosons. And so single electrons are fermions, but two electrons, then the spin becomes one, and they become bosons. So what they do when you lower the temperature, they undergo Bose-Einstein condensation, and that is called superconductivity. So these electrons can flow through crystals without resistance, which is already very remarkable, but this effect is actually 101 years old. So that is not so hot anymore. But then taking superconductivity and putting it into quantum devices, which are small, nanoscale, can give you very interesting effects. And some of them we will cover in this course. For example, you can build a superconducting qubit, which I think is one of the next slides. Okay. I think we discussed this very well, detailed enough for now, but I just wanted to say that this effect still remains one of the foundational, one of the most clear, these dramatic steps and important effects in the field of quantum transport, even though it's already 30 years old. And I will show you a couple more examples of experiments that really fascinate me or interest me because I also work on them, just to set the scope of the field. So this one is somewhat similar and also not so new. It is from 1998, and it is very important because it shows, again, quantization of conductance as a function of gate in this case, but now it is in a one-dimensional system. Yeah? This system is called a quantum point contact, and it is a narrow channel in a semiconductor. Here you can see the side view. Electrons actually live 100 nanometers underneath the surface, and there are gates on top with which you can, if you apply negative voltages to them, you can deplete electrons here and here. So where yellow parts are, there are no electrons underneath. And so electrons are forced to go through this channel. So you apply a source and drain bias here. It turns out that if you measure conductance, it is quantized. And that has to do with electrons propagating through this as completely uninterrupted ballistic waves. And then the conductance per wave is a quantum of conductance. And so if 2 waves can go through, it's 2 quanta of conductance. 3 waves, it's 3. And this is a beautiful staircase of conductance. This data is from Delft, where I worked. I'm very proud to have worked for the people who have measured it. So Leo Kouwenhoven, my boss from Delft, he was a master student on this project, and according to him, he was the one late in the night setting up some scan, and this kind of staircase showed up. So it must have been amazing to see something like that early on in the career. And this remains one of the most important quantum transport effects to date. Now let's jump 20 years to the future, and go from foundational effects to recent developments, and this is I would say a set of tour de force experiments that show ultimate quantum control over spins of single particles. Yeah? So again, I did not explain these semiconductors yet, but just think that in this island defined by these gates, you can confine a single electron. And so what they've done here is they've measured the spin of that single electron using a transport measurement. Yeah? So what the data is, it is a certain time-dependent pulse, like this, applied to a certain gate, and maybe it's this gate, and then they measure current through this sensor. And depending on whether electrons is there or not, the current is higher or lower. And that is what gives you these pulses. And this little blip here, this little blip is a detection of a single spin of a single electron. So basically, if the spin is in a certain direction, let's say up, then it can escape from the dot, and that gives you a blip. And if it's spin down, it cannot escape, and then there is no blip. So whether there is a blip or not tells you what the spin was of that electron. Then this second experiment is not just a readout, but it's a control over single spin. In this case, they took this kind of structure and they put over it a little coil to create a magnetic field. And they have applied a microwave frequency at the Larmor frequency of the spin. And so they have induced rotations of the spin. And so you can rotate from the spin being down, so cannot escape, to spin being up and can escape. And so when you measure a current, as the spin rotates, you observe these oscillations. These are called Rabi oscillations. I will explain what they are later in the course. For now, I just want to show you that they were able to control the orientation of a single spin, and actually in between these wiggles, what they are creating is a quantum superposition of spin up and spin down. So this single spin is not just a spin, it's a single spin quantum bit. Can be used for a quantum computer. And finally, this experiment, they have made two copies of this one to isolate two spins coupled together. And by bringing them close and far apart, they were able to rotate from both spins pointing up to spins pointing in the opposite direction. So go from singlet to triplet. And that shows that they can not only control a single spin, but they can couple and control the quantum state of two spins. Yeah? So if you continue going this road, you can build a whole quantum register of spins which you can control with voltages on little gates. And by now, I know that they're already at 4, and they're going forward with this. Yeah, so this is an example of an experiment where we, again, scale, like in that example with a transistor, right? We scale down to a single particle, single electron, and we control a single degree of freedom, a single spin. There is a very interesting other extreme. Can we control big objects? Yeah? Can we make big objects behave quantum mechanically and make superpositions of things like Statue of Liberty? Well, no. But in the field of quantum transport, there is another famous example. This is also from Delft, where they have created a quantum superposition of an electrical current flowing clockwise and counterclockwise in a loop. So what you see here is a metal loop. It is actually a superconductor with some tunneling junctions. So this is a little bit special loop, but in essence, it is a loop with a certain inductance, and they've isolated it from the environment and cooled it down to low temperatures, such that the current that circulates here can circulate in two directions at the same time. And the number of particles that participate in this current is in the billions. billions of electrons flowing clockwise and counterclockwise at the same time. So some people consider this as an example of macroscopic quantum coherence. Although this is a disputed point, because again, this dimension is 1 micron, and you have seen before that there are many quantum effects that manifest themselves at this length scale. So again, these oscillations is where they let the current evolve, and then after some time they measure, does it flow this way or this way? And they get when it's red, it's flowing this way, and when it's green, it's flowing the other way. As a function of time, there is this quantum Rabi evolution of current. And this circuit here is a detector. So this is what measures this current, and it is called a SQUID, superconducting quantum interferometer device. Okay. I think we should stop here, and we will continue on Wednesday.